All right, welcome everyone to the next edition of the New York Combinatorics Seminar. Today we're happy to have Katherine Perry from SoCA University, who's going to tell us about symmetry breaking in trees.
All right. Hi, everyone, and thank you so much for having me. And I guess I actually should have said this maybe before the recording started, but I should go ahead and just warn everybody that I'm staying with a very poorly behaved and loud golden retriever. So if you hear barking in the background, my apologies. Okay, so like Deepak said, I'll be talking about symmetry breaking in trees. And I'm from SoCA University of America, which is a small liberal arts college in Orange County, California. And everyone is welcome to come visit anytime you'd like. And this is a project that started at the Masamu Advanced Study Institute. And this is a program that every November we meet in a country in Southern Africa. So this was in Pretoria, South Africa, but this year it's in Angola. And the goal is to facilitate collaboration between mathematicians in the United States and also mathematicians in Africa. And so there are a bunch of different research groups. So there's a graph theory group, but also financial math, algebra, analysis, things like this. And I've been participating since 2016, actually. The leader of the graph theory group, at least one of them, is from Auburn University, where I went to grad school, and kind of the creator of the whole program is also, this is Overton Jenda, also at Auburn University. Um, but anyway, oh, and I'll add one other special thing about this workshop is that undergrad students, grad students, postdoc, faculty are all able to come. And so this project, you can see a few people have arrows with their affiliations, and it's because they were grad students at the time and have since gotten jobs. So Calum Buchanan is now doing a postdoc at the University of Denver. Peter Dankleman is at the University of Johannesburg and was actually also just at SoCA visiting us a couple weeks ago. Isabel Doris is now at Rice University, formerly Auburn. Paul Horn is my former postdoc mentor at University of Denver, and Emily Rivett-Carnac it was a grad student at University of Johannesburg at the time and is now teaching math at a high school in South Africa. Okay, all right. So the initial question that we were looking at is how do you measure symmetry in a graph? And so at the core, this is what we were interested in looking at. And so, if a graph is asymmetric, meaning no automorphisms, then you can say, okay, this graph has no symmetry. Um, and then you have, of course, on the other end of the spectrum, you have complete graphs, which have all the symmetry. And so the question is, how do you measure what's going on in between? And so, I have some graph G. Does it have a lot of symmetry? Does it have a little? And how can I measure something like that? Um, and so, also just, I should say too, if you have a question, please interrupt me at any time. But just like, let's recall the definition of an automorphism of a graph. And so if you have an edge in G, then your automorphism is going to map that to another edge. And maybe something else worth mentioning is that any automorphism will also preserve distances. Okay. And so what I want to do next is define two symmetry breaking parameters. And then the core of the talk will be focused on relationships between the two. So if I know one, what can I say about the other? That's sort of what I'm interested in. But both of these parameters give us a way to measure symmetry in a graph, but just in a seemingly different way. So the first one I want to mention is what's called a distinguishing coloring of a graph. And this is a not necessarily proper vertex coloring of the graph, whose color classes are preserved by only the trivial automorphism. And so I have two examples here, so a cycle and then this tree. And both of these graphs are what I would say we would call them two distinguishable, meaning if I place two, or if I use two colors, I can color the vertices in such a way that if I insist all of the green vertices need to stay green, then now only the trivial automorphism will do this. So originally in the cycle, right, we have, rotation, flip, and combination. But now if I say, okay, well, the green color class has to stay, on these three vertices, then I no longer have any automorphisms besides the trivial automorphism. Okay, does this make sense? Okay, perfect. Okay, and then with distinguishing, uh, of interest typically is what's the minimum number of colors that you can do this with. And so maybe I'll go back here and point out with this cycle, is my mouse visible? It is, right? Okay. Yeah, if I colored this vertex green and this one orange or something like that, then those two are effectively pinned in place. And now again, the only automorphism is the trivial one, but I've used three colors total, this sort of white color and then green and orange. And so, so you can do this, and I'll talk about why you might want to do this later. But in general, people are interested in what's the smallest number that you can use. And this is called the distinguishing number. And we'll denote it with this D of G or just D when it's clear what we're talking about. And this was introduced by Babai as asymmetric coloring in the 70s and also by Albertson and Collins as distinguishing number in 1996. Okay. And okay. And now I'm going to define something not using the definition that anybody else uses, but using the definition that goes nicely with this talk. And then I'll say what the formal one is, like the real one after this. But basically, what I want to do is I want to take a fixing set and okay, let me pretend that this vertex on the left is purple instead of green. And what I'm after is a distinguishing coloring where all of the color classes, oh, actually, I can even do that. Okay. Yeah, okay. Perfect. Okay. I didn't plan it for purple to be the one that popped up, but okay. Okay, but anyway, so if all of the color classes, except for this one sort of larger neutral class, if all of them have size 1, then, like I said, each of those vertices we can think of as being pinned in place. And the minimum number of vertices where I can have a distinguishing coloring with this property. This is what's called the fixing number of the graph, and then these vertices make up what's called a fixing set. And so I define it in this way because what I want to show is that there's a relationship between these two parameters, but they were actually introduced separately and with different motivations. So, okay. Let me see. Okay, so formally, what you would say is that a fixing set of G is a subset of the vertices, which is fixed pointwise by only the trivial automorphism. The fixing number is the size of a minimum fixing set. But the way that I really want to think about it is this distinguishing, like a coloring where everything, all the color classes have size 1 except for this larger color class. And this parameter was also introduced independently 3 times by multiple authors. So Harari in 96, Boughton in 2006, and Behavis and Mohair in 2004. Okay, and In the literature, you'll see this under determining number and rigidity index. And typically, actually, most of the researchers that have worked on this in Africa have used fixing number. And we also thought that having distinguishing with D and determining with D was like too much. So okay, we used fixing and distinguishing. Okay. Questions about either of these definitions? Okay, perfect. Okay, the whole talk is about them. So if there are any questions, please interrupt and ask. Okay. And so this tree will end up being important. That's why I kind of keep going back to it. But just, okay, again, this one is purple. And just so we can kind of see. So this tree is too distinguishable. I can have this distinguishing coloring with it. But my minimal fixing set is size 4. Okay. Okay, so now that I have introduced these parameters, let me say what the plan is for the rest of the talk. So I've introduced these things, but now I want to motivate why we're studying them, why looking at symmetry is important. And what I want to do then is pick a particular setting, which is looking at trees. And I'll mention, I guess, a couple of times throughout the talk, maybe why it makes sense to narrow it down. Okay, so I want to look at this for trees. And then I want to motivate a question. I want to answer the question, and then I'll provide some future directions. So, okay. Okay, so the first set of sort of motivation for why I want to look at symmetry breaking, besides giving us a way to measure symmetry, where we're headed is looking at both of these symmetry breaking measures together. And so one main and nice motivation is the relationship to the graph or graph isomorphism problem. And so understanding what breaks symmetry is actually related to designing efficient algorithms for determining if graphs are isomorphic to each other. And along with that, it turns out you can find or bound both the distinguishing or the fixing and or the fixing of a graph when the automorphism group is not known or not well understood. And so what we want to draw from this is that actually um, we can find these parameters without classifying all of the automorphisms. And so when you think about, well, how do I measure symmetry? Maybe the first inclination is to just say, okay, well, what's the automorphism group? And, this is going to be what I'll use to measure it. And here, what I'm saying is that actually we can do this and it tells us something else. Okay, or maybe I can't find the automorphism group, or maybe it's quite complicated. I can use this instead as another measure and maybe a more accessible measure to talk about symmetry. Okay, and then also along those lines, graphs with the same automorphism group can actually have different distinguishing and or fixing numbers. So even if you know the automorphism group, you can't just say, oh, well, okay, this is the automorphism group, so the distinguishing number is this, or the fixing number is this. So again, these are telling us something different. Okay. Okay, so that's my motivation for symmetry breaking. But I want to look at this uh, on the class on trees. So not just general graphs, but I want to focus in on trees. And one motivation for this that's not mentioned here is just I like trees. I guess one of my first projects was about rainbow spanning tree decomposition of complete graphs. So I'm familiar with trees. I like them. I think they're a beautiful class. And so, and general graphs is like too wide for what we're after here. And so, but interestingly, if you look at trees, oh yeah, actually I'll say too, um, with both of these symmetry breaking parameters, a lot of the results are just distinguishing for, this class or fixing for this class. And so the idea of sort of, okay, I want to look at maybe a large class, but also the combination, like what can we say about both of them? And so, okay. First, so yeah, so first thing is there's a nice algorithm for computing the distinguishing number of trees. This big O n log n time algorithm. And actually, I'll say too, this was extended to planar graphs as well. And okay, also, there's a nice result of Irwin and Harari, which says that you can always find a minimal fixing set of trees consisting of only leaves. So, okay, so in other words, if I can fix the leaves of my tree, then I can fix the whole tree. Okay. And then also recently, there was a result by Alakani and Sultani where they characterized all trees with distinguishing number two and radius less than or equal to three. And I'll say for radius equal to two, the method was they just listed all of the trees. And then I think this paper has some other results too, kind of with larger radius. But maybe I'll start here. And seeing this result was sort of the one motivation for the direction that we took. Okay. And okay, so even though when I was defining fixing number, I said, okay, here's this definition in terms of the distinguishing number. But this, like I said, this is not at all how they were introduced. So the two were introduced separately and with, different but similar motivations. But just because that's the case, there are obvious relationships. So in particular, the way that we can define or we can define fixing in terms of distinguishing allows us to find this upper bound for distinguishing number. So here with this cycle, like I mentioned, so we know the distinguishing number is this, it has distinguishing number two, but if I fix these two vertices, we can view this as having one orange vertex and one blue vertex. So this is a distinguishing coloring with three colors. And so I can use this method by having all my color classes have size one, except for this large color class. And so I would find those vertices, the ones of color of size one, with a fixing set. So I take my fixing set, I put everything in there. Um, I give it a unique color because I know if I insist that those vertices are fixed pointwise, then only the trivial automorphism remains. And in order to fix them pointwise, I can just say, okay, well, this vertex is in my fixing set. If I make it the only blue vertex in the graph, then it has to stay there. It has to be fixed. And so, okay, so I have my fixing set. They all have a different color. And then everything else gets this remaining neutral color. And so this is this upper bound. Okay, so I can bound distinguishing by fixing. And it turns out I can also bound fixing by not the distinguishing number, but by the number of vertices that are receiving new colors. So take a graph, say every vertex has one color, and then I want to place this neutral color. And I want to place a distinguishing coloring on this graph. And so any vertex receiving a color that's not the neutral color, okay, I'll collect those. And the complement of this, if I insist that this is a fixing set, then I can bound that is a fixing set, and I can bound that by this complement. So, okay, so what do I mean? So here's my distinguishing coloring here, these colors, and okay, these sets have equal size, so let me just pick one. The complement of that will be a fixing set. Okay, is it the minimum fixing set? Not necessarily, but it will be a fixing set, and that's what we're after. Okay, and same here, right? So I know that with the cycle, the distinguishing number is two. This result gives me three. So it's not perfect, but it is a bound. So okay, so what I'm after is that there are relationships. Um, and so both bounds are tight, but they are also arbitrarily far apart or can be. And so then the question becomes kind of uh, in the setting of trees, can we say something more about the relationship between fixing and distinguishing? So not just these two bounds, but if I provide some more information, and in this case, it was the class, then what can I say? Okay. And again, okay, this vertex is purple. Okay. Any questions? Okay, great. Okay, and so what we were able to prove is that if T is a two distinguishable tree of order at least three, then it turns out that the fixing number is at most 4/11ths of the number of vertices. And so we thought about this sort of, I guess we call this the fixing density. So what percentage of the vertices are we fixing in the graph? And I'll talk about what happens when um, D is greater than 2 as well, but 2 ended up being the most interesting. So when D is greater, the extremal examples are stars. But here this is not a star. Okay. Yeah, so we have this tree, which is two distinguishing, and then it has fixing number 4, and there are 11 vertices in this graph. And so this is the tightness example, or the sharpness example. Okay. So in order to prove, yeah, I know this is a lot of text. I'm just going to talk everyone through it. Okay, so I have a couple of lemmas and then an actual proof by picture of this is what's coming. And so the first thing that we looked at is what I am calling the all or nothing lemma. And what is important here is this text in the green that's at the bottom. So if T is a T distinguishable spider, and so by spider, I just mean a graph with sort of at most one high degree vertex. So one vertex of degree, at most one vertex of degree 3 or greater is what I mean. So, okay. And so if T is a D distinguishable spider, uh, D greater than or equal to 2, with maximum fixing density, then the number of paths that are coming off of the root with K vertices, either I have none of them or I have as many as I possibly can. Okay. Does that make sense? At least what I'm saying. Okay. Um, okay. So what this tell or what the way that we use this actually is to then say, okay, I have some tree and I want to find out, sort of what's the worst case for this fixing density. And this tells us that, okay, either if I have my sort of root of the spider, so the vertex that could have degree 3 or more, the only one, I have all of these paths coming off of it. And for any path length, 1, 2, 3, 100, I either don't have any of them or I have as many as I possibly can. This is full. And there can be at most D to the K of them because of the different ways to put a distinguishing coloring on this collection of paths. Okay. Okay. And then the next thing that I want is I want a base case. So instead of just saying, okay, I have a two distinguishable tree, let me suppose I have a spider. I just have one vertex with degree at most, or with degree that could be, 2, 3, 4, 5, like, okay, everything else has degree 1 or 2, and then this one at most with a high degree vertex, then the fixing density of this is at most 4/11ths. And I can use it with this all or nothing. So 2 to the 1. So I said I have 0 or D to the K. Okay, so in this case, D is 2. And so here I have 2 to the 1 and 2 to the 2 is 4. So this is the most I can have, and there it is. Okay, and then this has fixing density for, or yeah, fixing density for 11th. Okay. Okay, so when I have general graphs, or sorry, general trees, I'm going to fix my, so I know I want to say this is distinguishing number two. Okay. And our result is going to say that this has fixing density 411. So I know this graph is two distinguishable, and that will tell me that I can fix, or I need to fix at most 4/11ths. Okay, so here is my two distinguishing coloring of this tree. And so, okay, in general, I'm assuming I have this. And then uh, following that, the first thing that I'll want to do is I want to find all the high degree vertices. And by high degree, I mean three, yeah, three or more. And I want these to be vertices that are ends of pendant paths. And so by pendant paths, I mean one vertex is going to be a leaf. So for example, here's a pendant path. So here's a vertex that's a leaf. And I'm going to take this path and I'm going to follow it until I get to a vertex that has degree 3 or higher. And same thing. And so these ones all kind of meet at this vertex. So I'll identify this vertex and I'll call this U1. And then same thing, U2, U3. This is also a pendant path, right? And same thing here.
Is there some reason the four-valent vertex at the top isn't labeled?
Yes. Yeah. So it's actually, yeah. So this is kind of, I'm going to think about this as the root of the tree, but also it's not an endpoint of a pendant path. So in this, yeah, I guess in this example, I'm following all of my, I guess I'll start with a leaf and then I'll go up until I get to a high degree vertex. And the only way, yeah, I guess actually, yeah. So you could have it be the case that I have some sort of pendant path on that goes to there. I just don't in this example. Does that make sense? Okay, thank you for asking a question though. Okay, yeah, so you can have that. That won't make a difference though. Okay, I would still do the same process. I would have a pendant path on there, and I would identify it as one of these sort of special high degree vertices. Okay, and then the next thing that I want to do is I want to group all of these pendant paths that are going towards their special vertex. Okay, so here's this vertex, and it was the endpoint of three pendant paths. So I want to group those vertices. And what you'll notice is that each of these things that I grouped is a spider. So with at most one high degree vertex, of degree, I guess, 2 or greater. And okay, I guess okay, at most one, yeah, at most one high degree vertex. And the plan that I want to do is I think this is even here, yeah. So I want to claim a couple of things. So first, I want to claim that each of these graphs, these sets, like so, this is U1 and I have S1 paired with it. And my claim is that this graph here, on its own, not in the larger graph, just looking at it isolated, is too distinguishable. And this is true based on that lemma. So if I have at most one high degree vertex, and my then I can argue that if the original graph was too distinguishable and I'm looking at this piece, then it is also too distinguishable. And one thing I should mention too, actually, so when I say like too distinguishable or de-distinguishable, uh, that means, okay, there's a distinguishing coloring with this value. And so here, when I look at this piece, for example, or this collection, This graph is asymmetric. So actually the distinguishing number of this S2 and S3 is actually 1. Because it's asymmetric, I can just place one color on here. But this is fine. Okay, so if a graph that has distinguishing number 1 has a 1 distinguishing coloring, but it also has a 2 distinguishing coloring and a 3 distinguishing coloring, and so on. I'm just using extra colors. So in this case, I have this coloring without the distinguishing number, but this is still fine. Okay. And so, um, excuse me. Okay, so when I do this, I have sort of um, 3 things that are going on. So the first, uh, when I look at these SIs, if the number of vertices is greater than or equal to 3, then this lemma, this base case lemma applies. I can say that this graph is too distinguishable, and I can fix it by fixing at most 4/11ths of the vertices. And if it's asymmetric, then I do need to account for the fact that I have multiple copies of the same asymmetric graph. And so if I were to say, oh, this is asymmetric, so I don't need to fix anything, that's not actually the case, because if I don't fix anything here, then there would be an automorphism between these two pieces. And so we'll say, okay, if the graph is asymmetric, then the cardinal or the number of vertices is at least 7. So let me just fix 1/7 of them and just call it, okay? Okay, and then if the size is less than 3, then the situation that we have is something like this. So this is what we called a lonesome dangler. And what you can argue is that if you can find sort of two pendant or a pendant path uh, in the graph. So you have, I guess, one here, and I'm going to follow this path down along to another one. And I just am picking one arbitrarily. But what you can argue is that because I fixed everything else in the graph, the path that this lonesome dangler is on is fixed itself. And so that gives me that this U4, sort of the root of this path or the endpoint of this pendant path, is also fixed. And so because when I have size less than 3, I only have this structure, then this one is fixed by default too. And so then I get that each piece of my graph is fixed, and or at least each of these SIs. And there could be other vertices here that are in the graph. But it turns out that the union of the fixing sets of the SIs fixes the entire graph. And so maybe the way that I think about this is this result of Irwin and Harari, where you say kind of, oh, I can find a minimal fixing set that's just leaves. And so when I look at this graph, I have these circles that are kind of at the end. And so I fix the bottom pieces of my graph like I fix the leaves, and this sort of extends up to fix the entire thing. Questions? And then, like I said,
Catherine, I have a question.
yeah.
The result of Harari and Irwin
Mm-hmm.
Is a little bit different from the result that you're using here. You're using that once you fix the leaves, that you fix the whole tree.
Mm.
That's not equivalent to saying that there's a minimal
Yeah.
distinguishing thing, right?
Yes, that's correct.
Okay, just
Yeah. So I guess I should say I'm using this maybe as a way to sort of give I guess intuition to understanding. Their specific result was not used with this result.
Okay.
Okay. Yeah. Okay. Other question? Okay. And then we can also look at the case where the distinguishing number is greater than 2. And then in this case, like I said, it turns out that the star is the extremal example. And the proof for this is effectively the same. So you have a base case where you just have at most one high degree vertex, and then you can build this tree, or look at just a de-distinguishable tree, and then find these pieces that are de-distinguishable. And I'll say that the only difference uh, is in size. So these sort of lonesome danglers can have more vertices. So when you're looking at 3 distinguishable, you can pull off a piece that has like 2 of these, things like this. But the argument for why the whole graph is can still be fixed with this d minus 1 over d plus 1 times the number of vertices, it falls out very similarly. Okay. Okay. And so just to recap, so for graphs that are 2 distinguishable, we have that the fixing number is bounded by 4/11ths of the number of vertices. And when the graph is de-distinguishable, d greater than or equal to 3, then the fixing number is bounded by this d minus 1 over d plus 1 times the number of vertices. And it's worth pointing out that these bounds don't hold for de-distinguishable graphs in general. And so one future direction is to look at general graphs, or maybe another class, or if you add in some other parameter, then what else can you say? Okay. And so one other direction that we took was motivated by this result of Al-Khani and Sultani, where they characterized all 2 distinguishable trees with radius at most 3. And what we observed is that, so they had this really nice list, or this table with all of the 2 distinguishable trees with radius less than or equal to 2. And what we noticed, the largest graph in their collection was this one. And what we noticed is that every other graph that was 2 distinguishable, radius less than or equal to 2, was a special kind of subgraph of this one. And so what I mean by special is we call this a branch subgraph. And it's a subgraph where I'm going to take this vertex here, this root, and then I'll take some collection of these components coming off of this. So think about it. If I take this root and I delete it, then I have 8 components remaining, each of these pieces. And so so when I'm looking at these special subgraphs, what I want is this vertex, some collection, some subset of its components, along with this edge here that connects them. And so in particular, here I'll color this orange, not because it's this distinguishing or like distinguishing coloring, not because it's a fixed vertex, just because I want to be able to talk about it. And so here, if I take this vertex, then these are examples of some branched subgraphs of this graph. And so it was this idea, which led to this direction research. So observing that you could do this. And so what we were able to show is that if D and R are positive integers, and I want this distinguishing number greater than or equal to 2, then there exists a rooted tree, which we call TRD, and this contains all D-distinguishable trees of radius at most R as branched subgraphs. And I'll mention here, this is not an if and only if. So if I take a branch subgraph of this, then that doesn't necessarily mean that it's 2 distinguishable. But if I have a graph and it's two distinguishable and its radius is less than or equal to r, then it is a branch subgraph of this. Okay. Okay, and then this is just the statement of the proof again, and this is the construction. And so effectively what we do is we have this recursive construction. And if I'm looking at a de-distinguishable graph, then for example, and this is going to be my root, I can have at most d of these sort of singletons. So basically, however many of these I have, I'm looking at a star. If my graph is d-distinguishable, then I can have at most d of them. If I have d plus 1, then I would need d plus 1 colors on the leaves. And then same here, I can have at most d squared, and here d times d choose I for each of these lengths. And basically this is saying, okay, how many can I pack in here? And okay, so I do this, these things get really large. And so in our paper we have I think though we have this drawn out for maybe I think like maybe 3 distinguishable and radius 2. But the important thing to mention here or to observe is that by using the universal trees, then we can conclude that there's this maximum degree that they can have. Okay, and then in terms of this, so yeah, so our de-distinguishable trees are these universal trees. We have a fixed distinguishing number and a fixed radius. But a nice area of research is looking at, if you have a collection of trees with n vertices, sort of what's the minimum number of edges needed in an n vertex universal graph. So this is for all trees, and we can ask this question but redefine it just for, instead of looking at the radius, just de-distinguishable graphs on, or de-distinguishable trees on n vertices, then what would a universal graph look like in this context? Okay. Okay, and then, okay, I think I have a few minutes. So let me just say one other area of interest related to looking for relationships between distinguishing number and fixing number. So recall that we have this bound. So distinguishing number is bounded above by the fixing number plus 1. Here's our example. But like I mentioned too, there's nothing wrong with using more colors than the distinguishing number of colors. And so one question you can ask is, what happens when I do that? So this cycle has distinguishing number 2. And you'll notice that when I'm looking at a 2 distinguishing coloring of C6, I have 3 vertices that are colored orange. However, if I said, okay, well, what happens if I use more colors? Now I can find a 3 distinguishing coloring where only 2 vertices have this non-neutral color. And so this row here denotes what's called the paint cost of a distinguishing coloring. So here's the paint cost of a 2 distinguishing coloring. It's 3 vertices. 3 vertices have these non-neutral colors. And here, the paint cost of using 3 colors has 2 vertices have these non-neutral colors. And if I'm coloring with, okay, in this case, if I color with 4 colors, I'm not helping myself any. Like I would just have this 4th color, and either if I insist I place it somewhere, then it's completely unnecessary. Or if I say, I mean, this is also a 4 distinguishing coloring. I just haven't used all 4 colors. So really, the sort of range that it makes sense to look at is a distinguishing coloring using the minimum number of colors, like this has to be at least D, up to using the fixing number plus 1. And so I have sort of these two ends of the spectrum, but you can also look at what happens along the way. So is this, and this, there's pretty much nothing known about this. So is it monotone increasing? I guess it's known that it can't decrease. But then the really nice question of this, which is not mine, I can't take credit for this, but this is a question of Deborah Boughton, who asked sort of, when are these two things equal? So when does it not make sense to use extra colors? So when is the cost of coloring with a distinguishing coloring equal to the cost of using this fixing set plus one? So basically, when is the cost of distinguishing the same as the fixing number? So what kind of graphs have this property, which I think would also be a really nice area to look at in terms of relating these two symmetry breaking parameters. Okay, thank you very much.
Great. Thank you.
Thank you.
Any questions?
So if you impose additional special restrictions on the trees, let's say that they all are, all the vertices or leaves are k-valent, or that there are no vertices of degree 2, which turn out to be an interesting aspect of trees for other matters. Do you have any results of that extend to these special classes?
No, I think, yeah. So, yeah, like I said, most of the results in this area are about these parameters separately. And so, sort of, this is, at least on trees, this is the first one looking at the two together. And so we just looked at what can we say about trees as a whole and haven't narrowed it down.
And you alluded to the fact that you had extended these results to planar graphs. Is that right? Or
Not me, but so there's this nice algorithm by Chang where she looked at finding, yeah, the distinguishing number of trees. And then this was extended to planar graphs. So I think also independently, another group looked at this for trees as well. And then they sort of combined forces and then were able to look at find an algorithm for planar graphs, but that also might be a nice class to look at for this sort of thing. But
thank you.
Thank you.
Other questions?
Is the paper on archive?
It is on archive, yeah. Yeah, I guess it's linked on my website as well. So that might be the easiest way to find it, is just to find me and then find the paper.
Thank you.
Thank you.
Very nice talk.
Thank you. I guess it's your second time seeing it.
Anything else? All right, I'll stop the recording and then we can chat afterwards if we want. All right, just a second.